Thank you. Okay. Machine learning primer. Again, we're going to try to be very gentle with this. So if you have questions or something, please don't be shy because I don't want to lose anyone. Okay? We're going to talk about just a few general algorithms, common algorithms. And I want you guys, these are algorithms that learn from data. And I want you guys to get a good intuition, a good mental model of these. Hardly any math, but just really, when you walk out of here, you should be able to talk about these algorithms, have a sense of how they're different, and just, at least in your head, you get it. Okay, even if you don't know the math or anything else, that's not important, but you might know why I might choose this one versus choosing that one. Okay? And at the end, we're going to do neural networks. We're going to be very gentle with that because that can be a little bit complicated, and I think there is a talk either later or something maybe on deep learning. Okay, but the other ones that we are going to go through. People are still coming in here. Okay? The whole of machine learning is trying to identify some unknown function. That's the whole of it for almost every algorithm, is trying to identify some function that we don't know what it is, but we're trying to estimate that function and some relationship between x and y. Okay, and x could be a million features or one feature. Okay? This would be x and y. And we want to take input x to estimate y, to predict y. Okay? That seems simple, but that's just about every machine learning algorithm what it's trying to do, and you'll see that. Okay? Just about linear regression. Most of you probably are familiar with the equation of a line, y equals mx plus b, m being the slope and b being the intercept. That's largely what linear regression is. Now, those betas are learned from the data. There's nothing that you have anything to do with. They're learned from the data. And again, if there's anything I'm saying that you're not understanding, ask. I'm throwing out coefficient and those types of things. Hopefully, as we go, you'll kind of get some of that. So when we do simple linear regression, we're talking about usually just one feature. So you have an input x, you have the two learned coefficients, and you have the output. Okay, and I'll illustrate that in just a second. This is a line drawn through several points, and it's the line that's closest to every point. And the goal of linear regression, typically you're going to use linear regression when you want some type of continuous or quantitative output, and you're assuming that there's some linear relationship between the variables. Okay, so this is linear regression, and the way it finds that line is by trying to minimize the error. And the error is that line predicts that every point should lie on that line, but they don't. And so the line that you see is the error in the prediction. And the way those coefficients, the way this line is the minimum of that area, of that error. Okay, so it wants to be the closest to every point. Okay, and typically, let me see if I can do this real quick. Typically, that's done by what's called gradient descent. I'll give you an illustration of that here. So it starts off with a line, and it's continuing to calculate error. It's trying to identify the best fit line. That's linear regression. Okay, and again, it's a continuous output. And I'll give you an example in code in just a second. So you see the slope is slowing down with the intercept is continuing to be calculated. Again, it's the closest point to the line is closest to all of the points, minimizing the distance. Okay? Let's get an example. Let's say we want to predict lines of code, which is a continuous output. We use linear regression here. So we have gender, we have hours of pair programming, we have social accounts, and we have lines of code. Just some sample here. First thing we want to do, as some of you we talked about earlier, we want to convert gender to binary. Whoops, let me jump through this real quick again to get some of you caught up. When I'm saying features, those are features at the very top. Each one of those items or features are variables. Okay? That's your x. That's your y, your output or your target variable. Okay? And that's a sample. Okay? So we convert gender to binary. Almost every machine learning algorithm likes numbers. So we convert that to binary. So 1 would be female, 0 would be male. So given that, that's what the machine algorithm sees. Machine learning algorithm would see. That's your x, and that's your y. So if you're given 132, I'm hoping to get something close to 309. Okay? With multiple linear regression, you can see here. For every, with multiple linear regression, you want to say, what is the impact of x on y? If I wiggle x, how does that change y? So for example, for every 1 hour of pair programming, how many more lines of code do I produce? 9. You guys see what I mean? So it's weighted. It gives weight to the features. In other words, the pair programming is the most important here. Okay, and the same thing for gender. If it's a female, which is 1, you would just do 2 more lines of code, so it's probably not that significant of a difference. And the number of social accounts would actually take away a little bit from the lines of code. So that would be a multiple linear regression. Okay, let's look at one other example. App sold. You have an app. You're trying to sell your app. And what would happen if you didn't do anything? You didn't do any of those, X1, X2, or X3, what would happen? How many apps would you sell? 46. That's your intercept, right? So if all the other things are 0, you're going to sell 46 no matter what. But if you do $100 in advertising, you're going to sell 35 more. Do a public talk, you're going to do 27 more. A targeted podcast, you're going to do 52 more. So it weights, gives some weight to each feature, okay? And again, real quick, it's just polynomial regression. Sometimes you have a line where a line doesn't fit it perfectly. And by doing some higher order variables, you can kind of get a line that fits. But there's some other algorithms that are much better than that. Okay? Classification. Now, where the output is categorical. You're no longer doing continuous output. Now you're trying to say yes, no, male, female, good, bad, like, don't like. Okay? So most of the rest of these are classification algorithms, okay? Supervised. And when I say supervised, it means we have the answer key. We know what the answer is. We're going to train on the data because we know the answer. We're going to identify patterns in the data, hopefully that will generalize to data that we've never seen before, okay? So let's start with logistic regression. Again, get this. I want you guys to get this. As we move on, you'll see a lot of these have some things in common. Now, logistic regression, similar to linear regression. Even though it has regression, it's a classifier. It outputs a number, but it outputs a probability of belonging to a class. Okay? If it's greater than 0.5, it's going to predict it belongs to the positive class, whatever that is. You know, probability of going on a date or probability of not going on a date, whatever the positive class is. Okay? And if it's less than 0.5, it's going to predict 0. Okay? There's an intermediate step, which is Z. This is calculated. The other one was the sum of the squared error. This uses maximum estimation. And to try to get close to 0, 1, I'll explain that in just 1 second. So we have this intermediate step, which is Z. And logistic regression tries to squeeze everything down in between 0 and 1. Okay, because they're probabilities. And that's done using the maximum likelihood estimation. That's linear regression, could be anything. It could be negative numbers, can go all the way up to infinity, theoretically, where logistic regression is always between 0 and 1. Okay? This is the logistic function, so you take that intermediate step, just like linear regression, right? Which is, it's called the log likelihood, don't worry about what that is, but you plug that into the logistic function, and I'll give you an example here. Let's say that we have a bunch of resumes. And we want to predict who's going to get an on-site interview, who's not going to get an on-site interview, okay? And let's just look at some data here. We have gender that we have years of experience, interview source, phone screen, on-site interview, okay? Which is what you're trying to predict. So let's just go through this to straighten it out a little bit. We want to convert that to a number, binary. Years of experience is fine. Let me go. Because the interview source, one is more than 2 items, because again, what I was talking to in my earlier talk, if you average the number and it doesn't make sense, you have to use one-hot encoding. You can't average the interview source, whether it came from LinkedIn or from a friend or anything else. Averaging that wouldn't make sense. So you can't use those. Those aren't ordinal, okay? So we do one-hot encoding. And with one-hot encoding, it creates new features for each one of those, and only one of them is hot. There's a 1 only in one of them. So if you came from source 2, you can't come from source 1 or 3. Okay, so that's one-hot encoding. We're just trying to prepare the data for some of these algorithms. Phone screen is fine. Then we want to create our on-site, that's our target variable, to binary. Okay, let's say this is our data right here. Blue says you don't get an on-site interview. Green says you got an on-site interview. Okay, we want to create it with logistic regression, a decision function. And what a decision function does, it's linear separated. It draws a line and says if you're on this side of the line, you're a yes. If you're on this side of the line, you're a no. Okay, so that's what logistic regression does. Let's say this is what it came up with. Okay. Let's say just like linear regression, let's say logistic regression came up with this function. Let's plug it in and see. Okay. If it's greater than 0, we predict 1. If it's less than 0, we predict 0. Okay, so there's your decision boundary. But let's walk through a couple of points so you can get this a little bit better and understand the farther away from 0 you are, the more confident you are in your prediction. Okay? So don't worry about it. I'm just going to walk through this. Don't worry necessarily about the math, but you'll see. These are the 2 points. We're just going to plug that in real quick. You don't have to worry about the math. We plug in 2.5. Those are the 2 points. We do the math. 97% probability because it's way far from the line for logistic regression. Let's look at another point here. Same thing. You plug it in. 45% probability. It says it's a no on site, but it's a little unsure. Okay? So anyway, logistic regression tries to come up with a decision boundary, and it's a linear separator for classification. Okay? Support vector machine. Any questions on that? Okay. Support vector machine. Similar to logistic regression, a great classifier, but instead of giving probabilities, it's going to output a 0 or 1, and I'll kind of explain how that's done. But instead of the linear combination being greater than 0, it's a maximum margin classifier. So it expects being greater than 1 or being greater or less than -1. And I'll visualize that. So let's say here's some data that you have that you want to separate. It's pretty clearly separated. But logistic regression can separate this, right? That line separates it. That line separates it. But support vector machine is going to be as far away from the 2 classes as it can be. And it creates a margin. That's what a support vector machine. Very similar to logistic regression, but it wants to be it doesn't just separate it separates it with as much margin as it can have. Okay? And those vectors on the margin, on the dotted lines, those are called support vectors. That's partially how I got the name. Because if those vectors move at all, that margin has to move. If they come in, then that margin comes in. Any of the other points can move. But the points on the margin can't move, so they're called support vectors. Okay? And the line that separates the margin is called the hyperplane. You can allow certain things across the margin, or even you can determine whether you want something across the margin or even across the hyperplane. You can decide that, but it's still a maximum margin classifier. Real quick, I did some of this earlier, but I want to show you what happens when you transform your data. We're going to do some feature engineering real quick with the NFL Combines. And I'll briefly explain that again. The NFL Combine is kind of a showcase for college athletes to try to get drafted in the NFL. When they come, they do standing long jump, vertical jump, 40-yard dash, get their height, weight, and everything. And so can we take that data and predict who will get drafted? Okay, we use support vector machine here. So again, to do some feature engineering to show how you can transform your data, because height and weight are highly correlated, we want to combine those in some way. So we want to drop one of those instead of having 2 highly correlated variables. So here's what the data looks like at first, not separated. We take height and weight, and we look at weight over height squared, which is BMI. So we kind of combine those 2 features there. Same thing here, because in football you have really heavy people who may be slow, but they may be fast for their size. So we're going to take a 40-yard dash and convert that to a speed to size ratio. Try to get a little bit more signal, like I said, in our algorithm. Then when you do that, you might get some better separation now in your data. The problem is it's not linearly separable. But the great thing about support vector machines, they have what's called kernels. Don't worry about what a kernel is, but they have kernels that are great nonlinear classifiers. So now we've moved from linear classifiers, now we're getting more into crazy nonlinear classifiers where things are all over the place. And so depending on what the kernel is, depending on the shape of the kernel, let's say if it's radial, you create additional features that you can lift into a higher space. Now you can linearly separate it. So with the support vector machine, you can separate it. So you still have your hyperplane, you can separate it like that. Okay? Decision tree. Totally different classifier. It's a tree-based classifier. It uses basic if-then-else rules to classify. and we'll walk through it. Start at the root, and as you go down, it picks the next best feature that's going to give it information gain, and the most discriminating feature that it can pick will be the next feature. Give you an example here. Study on short-term attractiveness. Short-term attractiveness is when you walk in Starbucks, 30 seconds, 3 minutes, you see somebody. You can't factor in money, can't factor in personality, can't factor in influence, you just see them. And you sum them up as far as attractiveness. Research shows that short-term attractiveness, the most important thing is proportionality in the features. Average features are better than distinct features, okay? And symmetry is most important. Men were more attracted to women who had a waist-to-hip ratio of 7 to 10, okay? A BMI of slightly over 20. Women were more attracted to men who had a waist-to-hip of 9 to 10, and with body composition of 12. And everybody was more attracted to people who were well-groomed, okay? So let's look at that. Facial symmetry, which is the most important feature there. We have BMI, we have waist-to-hip, and we have well-groomed. Okay, don't worry about the gender there. Okay, so these are some of the features that we're looking at. This is the data. It's all over the place. You can't really linearly separate it. So let's look at this. Start at the top. Symmetry is the most important feature, so we're going to start there. It gives us the most information. Is symmetry greater than 0.8, with 1 being the best, greater than 0.8? If yes, let's continue to say yes. Then it asks, is BMI less than 25? If that's true, then it says, are you well-groomed? If you're well-groomed, it says you're attractive. If not, then it goes on and says, is your hip to waist greater than 0.84? If yes, then you're attractive. If not, then it says you're average. Okay, that's kind of how a decision tree works. It's totally different from the other ones. But it's a great nonlinear classifier, and I'll show you how that works. Here's our data. Now let's visualize those decisions. A decision tree separates segments of the data points, which are axis aligned. In other words, they can only be vertical or horizontal lines to separate the data. And in those segments are the classes. For example, through the first run through, you might see this. Those might be the classes. And as you get more information gain, that might be the class. You get a little bit more information gain, that might be the separation, which is a pretty good prediction. Okay? So you see it's totally different shape, but it's nonlinear, but that's what a decision tree does. Okay?
So there are multiple orders in which you can create the tree.
Mm-hmm.
So who decides that?
The algorithm would decide that. Depending on, again, there's some hyperparameter that you set, which I do not want to get into, but there's hyperparameter that you would set that would determine the information gain, what features are most important, what would give, once you determine one feature, what next feature you want to look at that would give you the most information, et cetera. So the algorithm would determine that.
And so the output will change, right? Depending on if we just change in the earlier example.
If you change what? I'm sorry.
Can you go back to the example?
Sure.
Yeah, here.
Here?
You're first checking symmetry and then the BMI.
Mm-hmm.
And if we first check the BMI and then the symmetry.
Well, it wouldn't do that because symmetry gives you the most information gain. It's the most important feature.
But we don't know that, right?
Well, we do know that. That's what I'm saying. We do know that. If it weren't, then it would be different. If BMI, or if you had a different population, or if you had all women, or if there were some other animals, or it would be different. But as far as humans go, symmetry is the most important.
I think it's based on prior research that the person that's making this had done.
Yes. Yeah. I'm sorry. I see what you mean. Yeah, because it's predetermined. Yeah. I'm sorry?
So, like, there are domain experts in financial.
Yes. Yeah, in fact, I'm sorry, go ahead.
Is it that the choice of this first fork here is made by the user or by the algorithm?
The algorithm.
It's by the algorithm.
Yeah, the user isn't going to say, well, I think BMI is, the algorithm would, by the data. The data would dictate that, not the user.
Categorize them is something that we're already considering an assumption before applying the method.
You're learning from data. It's the data. We could think whatever we want, but the data says something else, that's the answer. It's not what we think. The data says it's
Categorizing which feature are we going to prioritize, either symmetry or BMI?
well, the data is going to dictate that. The algorithm is going to tell you that. You're not going to pick, well, I think I'm going to do this one first.
The tree construction iterates over all possible features and picks the
Well said.
Something to point out is that there's two sets of data. There's your initial, like, calibration data, and then there's all the data that you run this through, right? So the calibration data determines symmetry at first, and blah, blah, blah. Sets up the algorithm, and then you use that algorithm for your research, right?
You're talking about like a training set versus test set? Or?
Yeah, right, training.
Perhaps, but let's just assume that this would be a training set. We haven't done any testing yet. But let me just kind of work through this, and then if there's other questions, so we don't get bogged down. Okay, yeah, thank you. Okay, let's get back to where we were. Okay, that's where we were. Nonlinear classifier, okay? K-nearest neighbor algorithm. Fairly simple, instance-based, and what it does, depending on what K is, and if K is, let's say, 3, then what it would say is when you plot the data, it's saying the 3 points closest to me are going to be the class that I'm in. So it's the majority rules. Okay? But first, let's talk about what distance is. I'm going to show you, it's just basic geometry. But let me show you when we say distance. Okay? You have the first one, A1 minus B1 squared, A2 minus B2 squared. Don't worry about any of this, but I just want to give you a sense of when we say distance. Because when you talk about high dimensions, it could be way out there. Okay, let's just say this is some data here, number of relationships pulled from the same study, and greater first relationship. Okay, this is our first feature vector, just looking at two features, 3, 7, and 6, 11. This is how we calculate distance, just really quick. Okay, those two numbers that are stacked, squared, sum, and the square root of the quantity. Okay, so but let's visualize it so you can see a little bit better how it's just geometry you learned in maybe junior high school. You have 3, square it, 4, square it. That's the squared distance. You take the square root of the sum, and you get 5. When we talk about distance, that's all we're doing. We're saying how far away is something from something else. Okay. Now, let's say this is our data. We want to do K nearest neighbor. Let's say we add a point here. Again, it's a non-linear classifier. We add a point there. We want to say, what class will that be in? Okay. Well, the 3 closest points are there. So what class is it in? Yellow. Thank you. Yellow. Okay. So that would be the boundary that just looking at this with K equaling 3. And it changes depending whether it's 2 or 7 or anything else. Okay? Quickly, study was done. Research was done in England, taking several pictures of people all over the world, different countries, averaging those pictures to say, this is what someone looks like in this country. This is the average way this person looks in this country. These are the average features. Same thing here for females. One thing that they found is that average is pretty when we average. Remember I said average is better than stark? So average makes people more attractive for one. But secondly, there's an algorithm I'm not going to get into called eigenfaces, which takes faces that's a linear combination of the eigenfaces. The point is it's just a point out in space. Your face would just be a point out in space. And your face would be closest to your own face. These were algorithms that were used before deep learning to try to do facial recognition. So the same thing here that was done to try to say, if I take a person, can I put them out there? What nationality are they closest to in terms of their features? Lithuanian, there was no Lithuanian in the study, but you can see these are countries that are close to Lithuania. And you have a person who's Chinese American, and when you say K nearest, or when you say actually K would be 1 in this case, the closest nationality to this person was Peruvian, then Chinese, and then Japanese. Okay, so K nearest neighbors is used in various ways. Okay, even in face recognition. K-means. This is an unsupervised algorithm. We don't have the answer key. We don't know, just like everyone in here. I don't know a lot about you, but if I had enough data, I could probably group you similarly, whether those who are students, those who work in a certain part of town, those who are born certain places, those who make a certain kind of income. I could probably group you on some features. That's what K-means tries to do. I don't know what website you go to, but I can group you and try to guess based on certain things and maybe treat certain customers differently. Okay, so that's K-means. Let me illustrate that real quick. Whoa, let me see if I can pull this out here. Real quick, let me just walk it through, then I'm going to show you. If there were 3 different people in this room that I said were team leaders, and I said whatever team leader you're closest to, you're on that person's team, right? Then I told the team leader to walk into the middle of whoever's on his or her team. Now you look around, whatever team leader you're closest to, you move on that team leader's team. Now that team leader moves in the middle of the group again. You continue to do that till no one moves anymore. That's K-means. Okay, and I'll illustrate it here. You start off with just some random points. Those are the team leaders, just random points. And now you tell everybody else, whatever point you're closest to, you're in that class. That's K-means. And then you say, those points are called centroids. You tell the centroids to move to the mean of all the points. Okay? Now you tell, who are you close to now? Now you're on their team. Okay? And now you tell the centroids to move to the middle again. And you say, well, who are you closest to now? And the centroids will continue to move. Green slightly move. I know it's probably hard for you to tell, until it doesn't move anymore. I'm going to do that one more time so you can see that. Again, points are randomly placed. Who are you closest to? Centroids will move to the mean. This is K-means algorithm, a version of it. Then based on who you're closest to, they'll move again. And again, this is an unsupervised algorithm. You're just trying to cluster individual by like features. Okay? I'm going to have to move along here because we start about 15 minutes late.
Can you use K-means with categorical data?
Well, no, it's unsupervised. Well, you can use it with any feature, but you would have to convert it to some numbers. You can't get a mean of a person's height. I mean, not a person's height, but a person's hair color or something.
Did the groupings change, right? Did any items, with the first round of K-means, you assigned everybody to one team or another, right? One group or another.
Right, based on where the centroid is, right.
Where the centroid is. Did that assignment change at all in subsequent runs?
Yes. Yeah, every time the centroid moves, it's closer to someone else who wasn't closer to. So you change, now you become green, and now you might be blue, and then when nothing moves anymore, that's your cluster. Okay. Neural network, just in time, about 8 minutes or so here. Neural network, which is largely state-of-the-art now, especially with deep learning. We're going to walk through some things here. This will be the only time we lose just a very little math, okay? Loosely based on the human brain, neurons in the human brain. But what I first want to do is look at a perceptron. And a perceptron is just really a node in a neuron. Just one little, if we back up here, just one node, like A1 there. Okay, that's a perceptron. And you see, you look at the bias, it's a linear combination, just like we've done with logistic regression, linear regression, support vector machines, weighted combination of the features. Okay, that's the input. The only thing, they're not learned coefficients, they're random at first, and it kind of learns from there. But that's the function. Okay, so let's look at the OR function here, which is kind of easy for it to calculate. The OR function says if I'm feature 1 or feature 2 or either one of them, then I'm a 1, otherwise I'm a 0. That's the OR function. Okay, and that would be a plot of the OR function, which can be separated. So let's do just a quick run through this, just 2 runs so you can see how it's learning, how a neural network learns a little bit. Here's our update rule. Now, this is the only time you have to pay. If you don't care about neural networks, ignore what I'm saying. If you care, this is an update rule, or an update rule. Okay? If the linear combination is greater than 0, you're going to predict 1, else predict 0. Okay? That's just like logistic regression and everything else, or support vector machine. Here's the update rule. If this is what the weight is existing now, if you're wrong, you're going to take the input times the output minus the target and subtract that from the weight. And you'll see how that's illustrated in just a second, okay? So let's say the first input is 0, 0. What should the target output be? Right. If we input 2 zeros, we should get 0, right? So let's say these are the weights, the initial weights, 3, -2, and 2. Okay, pay attention to the weight, because that's the whole of neural networks. Okay. Let me back up here. Okay, so here we go. So you have 3 plus 0, 0, right? It's just a linear combination. It outputs 3, so it's going to predict 1. Remember, if it's greater than 0, it's going to predict 1. Is that right or wrong? It's wrong. So now, again, this is neural networks. You have to update your weights. That's what neural networks do all day long. So here's what we're going to do. Just twice we're going to do this so you can get a sense of what's going on. Okay? Let me back up so you can see what I'm doing here. You're going to put in the weight, the initial weights. You follow me? Those are the weights that you had when you ran it the first time. Then you put the output. That's what you had when you ran it. Then you put the target, right, which is what it should have been when you ran it. And then what the inputs were when you ran it, which was 0, 0, and then the bias. Okay? That's what we just did. And when we do that math there, you see how the weights changed? The top weight came down a little bit. Okay? Neural networks are kind of like, I'm thinking about going to maybe at the doctor or something on a scale, although a lot of scales are digital now, and where you just kind of are tapping that weight until it balances. That's kind of what a neural network is doing. Okay, let's have one more run through. 2, negative 2, and 2. Don't worry about the math, but you'll see. It outputs 0, is that correct, or it's wrong? Okay, it's too low. So what's going to probably happen to the weight? If it's too low, what's going to happen to the weight? It's going to be tapped up a little bit, right? So let's see if we do that here. Again, don't worry about the math here. But you input the math. That's how the weights get updated. So can you see how the first weight bumped up a little bit and the second weight bumped up a little bit? Okay, that's what neural networks are largely doing. I mean, that's what a perceptron, that's a perceptron. Now, neural network is just a network of perceptrons, okay, which is also called a multi-layer perceptrons, a neural network. Okay? Let me do one other thing here if I can grab over here before we go. So you can get a sense here. You're feeding into the hidden layer here, and I'll explain that in just a second. And just like what we did, whatever the error is, which is called backpropagation, you're feeding back into the network so it can change the weights. And then you're doing that again until you don't get very many changes in weights. That's what a neural network is doing, but on a larger scale. Those are several perceptrons that are doing that here. Okay? Let's see if we can get through this here. The more layers you add, again, this is the power of deep learning. The more layers, you can learn just about any complex function. Okay, and I want to show you real quick. Well, let me just show you here. This is a fairly complex function that neural networks can do with no problem. But who is this? Who is that? Anyone? No? You know, instantly. Machines find that difficult, but not deep learning, because for the most part, if we can do it without reasoning it, there's not a lot of reason. We can just look at it. Deep learning can do it. And it's just amazing. The head's partly cut off, and it's black and white. They don't have a lot of the cues that we would normally count on. This is what the algorithm sees. We see that, the algorithm sees this. Okay, and it learns from that. I can't tell you how to tell the difference between a cat and a dog. I can see it, but I can't explain, well, if this happens and it has floppy ears, because not all dogs have floppy, I can't tell you what the difference between, but I know it when I see it. So does deep learning, which is amazing to me, that it can do a lot of these things. Oh, I don't know.
Because of that underscore, the black line.
I don't know. I can't tell you.
I can tell you.
Okay. Deep neural network, that's why it's called deep learning. I'm not going to get a lot into deep learning, but that's why it's called deep learning. The more layers and the more nodes, you can learn just about anything. It's very intensive in terms of learn that way, but that's why cars can drive themselves. And in fact, let me go one before we get out of here. Recurrent networks is a term that you may hear. They're great for speech, text, recurrent neural networks. Convolutional networks are great for photos, recognizing images and things like that. For example, the first layer may learn a feature, then the next layer may learn a feature of a feature, and then a feature of a feature, and it's just incredible how it can become so accurate. Deepface here, which is Facebook, which does some transformation, but it's 98% accurate, which is amazing, which is what humans do. 98% accurate. And there's 9 layers here for facial recognition. So when we talk about deep learning, because of all of the deep neural network, and finally, I'm going to stop with this one right here. It doesn't matter if the face is in shade, if eyes are closed, if you're wearing glasses, if your head is turned, it can learn it just like we can. Just because someone got a haircut or wears glasses, we don't think about it, and that's what deep learning can do, and that's all because of, with neural networks. Okay? Any questions? If not, I'm going to stick around. Anyone have any questions that they want to say while the group is here?